Hi everybody, welcome back. So it's been a while since I've looked at this. I've been out of town and just getting back onto it. So what we're going to do in this video is we're going to focus on the power supply of this amplifier. This is going to be part 2 of our series on the Marantz 250. Now, as I said in the previous video, there are really 3, we can even say 4 different types, different versions of this amplifier. This is the earliest one. This is just the straight Marantz 250. Now there's a Rev 1 and a Rev 2 based on the serial numbers, and those 2 revs, the purpose of it was to try to correct some of the inherent flaws in the design of this particular amplifier. The biggest thing was with the bias circuit. They changed that to try to make it more reliable. They changed the input circuit where your differential pair is. They added a constant current source to that, which was a good idea. They added some additional filtering to reduce the possibility of parasitic oscillation. And you have to forgive me, all the fans running in here because we got the air conditioning running and we have the oscilloscope and signal generators, all kinds of things on, so you'll be hearing some background fan noise. And they made some improvements to the power supply. Mainly they relocated the diodes, the rectifier diodes, to a second board that's on top of the capacitors. And the reason being is these tend to get hot when they're under high load. These are 400 volt 6 amp rectifiers. And that's pretty hefty for a axial lead diode like that. There are other options that are drop-in replacements, but they're special order and they're a little bit hard to get. You can find up to like a 10 amp 400 volt or 10 amp 150 volts, something like that, that would work in here. The whole point with all of this, though, it's really not about what the diode can handle. I mean, that's certainly part of it, but the biggest issue is how much current or how much power are you dissipating by this diode. What do you mean? What do I mean by that? What I mean by that is that, let's say we have 50 volts that we're rectifying. Okay, and we're using RMS right now, so that's the same as being 50 volts DC, right, as far as wattage is concerned. So let's say we have a 50 volt RMS signal going across this diode, and let's say that we are actually drawing 5 amps of current through the diode. Now we all know that a diode has a forward voltage drop, and on a standard diode that voltage drop is anywhere from maybe 0.6 to 0.7 volts. Let's say 0.7, worst case scenario. And that can change as you dissipate, as you draw more current through the diode. It's a kind of a moving target. But let's just say we have 5 amps and 0.7 volts drop. If you do the math on that, okay, let's just do it. 5 amps times 0.7 volts is 3.5 watts. So what's happening is each one of these diodes is dissipating at its maximum, let's say, 3.5 watts of heat. That's being dissipated as heat. And that heat can really heat up the legs of these transistors and kind of make the circuit board get kind of crusty. It can soften up the solder and loosen it on the board. And that's why they moved it up here, in the hopes that it will dissipate the heat a little bit better. Now, there's some options we can do for this. We can, I mean, just putting a heavier duty set of diodes isn't going to change it. If they're in the same case as this, they're still just going to get just as hot as these ones. Who cares if they're 10 amp or 20 amp or 50 amp diodes? If they're in a package that's this same size with these leads, you're going to have the same problem with heat. Even though it may not destroy the diode, it will still loosen it up and burn up the board and all those other things, and you'll have thermal problems. So there's a couple ways we could approach this. First thing we could do is we could use Schottky diodes, and there are such things. There are 10 amp Schottkys. Let's see if I can find one here. Yeah, here's one. So you can see these are 150 volt, which will be good for this power supply. They're rated at 10 amps instead of 6 amps, so even higher rating. And they're Schottky, meaning their forward voltage drop would be lower. Now that may tempt you to do that, because if you do the math, the lower the forward voltage drop, the lower the heat dissipation you're going to have to deal with. Because instead of 0.7 times your 5 amps, let's say, theoretically, now it's 0.3 times 5 amps, and now instead of 3.5 watts, it's 1.5 watts. Makes a big difference, doesn't it? So why wouldn't we just do that? I mean, these are faster switching and everything, right? Well, there's some drawbacks of using this. One of them is that forward voltage drop will change dramatically, more so than in a standard diode, as you increase the amount of current. So when you start getting towards that 5 amps or 6 amps of current, what's going to happen is that voltage drop is no longer going to be 0.3, it's going to be higher than that. And it could be a lot higher, it could be up over 1 volt, which kind of defeats the purpose of the heat, right? Because now with a 1 volt drop with 5 amps, you're now dissipating 5 watts of energy. So I hope you're following what I'm saying. The other thing is the reverse leakage current through these is worse than on a general purpose diode. So although these have very fast switching capabilities, you can get some reverse leakage as it shuts off. So this isn't exactly the ideal situation for what I would want. If this was a high frequency power supply like a switch mode, then these would be absolutely inadequate. They would not work, and they would burn up real fast, and these would work perfectly. But that's not what we have. We have a low frequency linear power supply. The other issue is all these little capacitors here, they all go bad, but those will just get replaced by default. Some of these carbon resistors will drift in value. We can replace those with metal resistors like metal film or metal oxide that won't drift with temperature and that won't drift with age. And last but not least is your protect circuit. This relay is very odd. What they've done is usually the back pins are going to be your coil, and then the front 3 pins are going to be your common, normally open, normally closed. Here's the thing, this one is backwards. The common are the back leads here, the coil is the second one down, then you have your normally open, then you have your normally closed. So these relays are wired different from a standard relay. Now there are some people that can that will rewire a normal relay, like cut leads inside the relay itself, and you know, but what I'm going to do is I'm just going to use a little adapter, and it's just a little board that lets you adapt this type of a relay to this type of a pinout, and it just uses a couple of these little standoffs that you can get cheap on eBay or whatever, just break them off, and then you can just pop one of these in. And what I'm using on this, you can use a standard what is it, an MY2 relay or an LY2. I am going to use an LY2Z relay, 24 volt, and it's a Z-0, and this all means that the pins are circuit board mount pins instead of the thick, socket mount pins or solder on pins. And I'm also going with the bifurcated contacts. Now if you look very closely, I don't know if you could see it, but there's 2 sets of contacts in there on each side. And what that gives you the advantage of is one contact is always going to touch the relay before the other. So one of them will take all the arcing, and it might get a little bit charred up, but the other one will stay cleaner. So these stay cleaner for longer, and they're less likely to fail if you have some arcs and so forth. So just another thing, if you look at my video on the Pioneer Spec 1 preamp, it has a speaker relay set up in it, and it also is using the bifurcated contact relays. So we're going to change that. So that's what we're going to do in this video. But first I want to talk about something from the last video about the amplifier. So if you recall from the last video, we found that this diode was really bad. It was really leaky. It is a germanium diode, and oh boy, I don't even remember what it was. It was a 1N. Was it 1N 157 or 152 or something like that? I don't remember. But it was a germanium diode, and these things are leaky and hard to find. I mean, I have some, but I'm not going to do this. And if you remember where I left off the video, I just tack soldered a UF1004 silicon diode in there, and everybody lost their mind on it. And this was like, hey, you can't do that, it's different, you know, it won't track. And so what I did to just kind of show you is I went ahead and I took that UF1004, I encased it in a little piece of heat shrink, I skinned off one side of the heat shrinks to expose the actual diode body itself, and then just put a little tiny dab of thermal compound on it and tucked it down in here just like the old one was mounted. And we're still using the original transistor here, and we have all the original transistors in here, no new transistors. And I really haven't even changed these small caps, even though we know they're bad. And let's turn the meter on. I have it connected across the collectors of the PNP and NPN transistor. So let me just show you where I'm connected. I'm connected from here, right here. I'll use my pointer because everybody complains about using your fingers to point. So from here over to here, okay, and in between there, if you follow it, you have this little 0.15 ohm resistor and this little 0.15 ohm resistor. So these are your emitter, or your, well, collector resistors, we'll call them, to your center tap, or to your center point, midpoint, which is where the speaker goes. You see, it goes off to the speaker terminals. And I'm just going to set this for about 20, anywhere from 20 to 25 milliamps across these two resistors. And really the name of the game, the voltage you set it to is not as important as making sure A, it runs cool, and B, we don't have any crossover distortion. I'm thinking, you know, that 20 milliamp or 20 millivolts is sufficient. So we're still connected up. Let's turn on, and you can see I have it connected like that. Let's turn on our meter to millivolt mode. All right, and let's back you way out. And I'll move the light out of there so it's not so glary. I'll turn on the power here, and let's power up the amplifier. Okay, and we should have a relay, and I do have a dummy load connected, an 8 ohm dummy load and a signal source. And we can see right now it's sitting at about 15 millivolts, and yes, I have the meter hooked up backwards, so it reads negative. That means nothing. We only care about the absolute value that we're measuring. So let's let that idle for a while, and I'm going to let this just sit for 10 or 15 minutes, and then we're going to come back and we're just going to see if it will hold. I'm going to let it warm up a little bit, and we're going to set it to that 20 millivolt range somewhere, and then we're just going to see if it holds its bias. Okay, this has been on for about 10 minutes or so, and you can see it's now stabilized somewhere around 18 millivolts. And you can see it's holding it. See, it drops down, then it comes back up. And it seems to be in its little happy place. Now, I said 20 millivolts. That's 2.5 millivolts off of that. That's pretty close. Let's see if we get any kind of crossover distortion or anything that we can see. So I have a, let's see, we're going to start out with a 100 millivolt input signal into the input jack. And we're going to run this, and if I back you up, you should be able to see the oscilloscope there. I may have to change the scale a little bit, but we'll see on that. All right, here we go. And let's move the... Now you can see there is absolutely no crossover distortion. Let me zip this in here. It looks pretty clean to me. It looks really clean, as a matter of fact. Now, of course, there's no, it's a very small signal right now. So let me go to times 10, and let's turn the signal up. And of course, now we're lighting up our dim bulb, because I have a 300 watt current limiting bulb, and there it just tripped the protect circuit. So I'll go down a little bit. Here we go. And you can see what kind of voltage we have across those midpoint resistors. If I turn the signal back off, see the signal goes away, and bang, it comes right back down. And it's sitting, we put some heat on it now, and yep, these are warm a little bit. This is a little bit warm to the touch now. And we can see we're just kind of floating here around that 20 to 21. And that's after adding some heat to it. And you can see it's already starting to drop back down a little bit. There it goes. So, as far as bias is concerned, there's no problems. And we're using the stock configuration of this bias circuit, which is scary in and of itself. So you can see, really the best thing to do would be to connect this endpoint to the wiper. And what that would do is, in the event that the wiper comes loose from the circuit, or like the wiper fails, this acts as a fail-safe. And this will keep everything from running away on you. Now, it's still not going to solve all the problems, but it will give you a little bit of safety margin. Now, if this transistor fails, or you lose your DC voltage here, the transistor will turn off, and this will still shoot up to the moon and blow your outputs. So this is still not a very good circuit. I don't know whether I'm going to rebuild it on this amplifier or wait for another one to do. We'll have to wait and see down the road here, because I might do a second one of these, and if I do, I'll keep this one kind of stock, and the new one will go to town on the design. Alright, so you've seen that. That's enough about the amplifier for now. Let's focus on the power supply. Okay, we're in the process of installing the relay, and I've removed the old one, and you can see it was badly damaged. See how it's welded? You can't even, it won't even click. This side will. This side will not. It's shot. So this is an example of this is unrepairable and has to be replaced. And here's the little board that does the adapting. And you can see it is double-sided. And it has plated through holes and everything, and I just dropped it on the floor. And if you don't want to get one of those bifurcated contacts, those are a little bit harder to get, you can also just use this standard relay. And there it is. And this is a Omron LY2-0 24 volt. If you can see it, there it is. Okay, and essentially you just take, where did I put those things? You just break off some of these, and you can buy these things on eBay or Amazon, or you can buy them at parts stores like Mauser and DigiKey. They just come in strips like this, and you just cut them off, and they go in the small holes. And then this just fits up here, and I'm not going to push it down in, but it fits very snugly in this way. And that allows you to adapt this type of relay to this type, because once again, here's your coil, it's going to this pin, and normally that coil would be connected to this pin. So just, you know, and then you don't have to modify the relay and you don't have to modify the board. Although I am going to make one little change on the board, and I'm going to show it to you now. Okay, putting the relay board in. I'll zoom you in a little bit so you can see better. You can see where the holes from the old connectors, or you know, from the old relay, you see how big these tabs are on this, are way too big for these pins. So what we have to do is make a little adapter. So what we're going to use is this little copper foil, and you can buy this at craft stores. It's very inexpensive for what it is, and it's copper. And you can see, let's see here, it says right there, you can see copper. And we're just going to take a little piece of this and cut it. Alright, I'll do this, try to back up and do this on camera if I can. So we're just going to cut a little piece off like this. And then we're going to cut it this way. And this is way too much, and that's fine. The next thing we're going to do is take a little backer board. This is just an old piece of wood, and I'll put this up on there, and I'm just going to use my little center punch, and I'm going to pop a hole in it just like that. And you can see it has the little push out on there, which we're going to use to our advantage here in a minute. And then we're just going to go around and nibble it until it's a little circle that's about the same size as the solder pad that we're going to attach it to. And again, you don't have to be perfect with this, just get it close enough to fit. I like to take those sharp edges off if I can. And there it is. So you see, we have that just like that. Then what we can do, and I've done all but 2 of them so far, is we can take this, push it down over here, because now we already have the hole. You can see it fits very nicely right on there. And if you need to trim a little bit more off, you can. Okay, I think this is going to be okay. Sometimes you have to take it off and trim it a little bit to fit, so you don't have it interfere with the pins next to it. And then we're going to go ahead and solder it in. See if I can do this on camera. Just like so. And it looks perfect. There it is. And I'll do the very last one, and the relay will be installed. Okay, looking at the power supply, this thing's pretty much shot. I'm going to need completely rebuilt. These 2 bleeder resistors here, and they are, where are they? They're 2.2K, I believe, at 2 watts. There's 2 of them, one here and one here. And I pulled them out because they're bad. Well, at least one of them's bad. The other one's technically okay. But you can see how tarnished the leads are, corroded, I should say. But going on this one, you can see that's about 2.2K. That one is good. This one, however, if it'll even read now it's reading open. It's open. Now it was reading like 7K. Now it's reading totally open. So this thing, and you probably didn't see that because I was off camera. So this thing actually has got a lot of problems, and it seems like things were shorting out in here and people were just letting it go like that and kept playing it. Luckily, I have 2 metal film resistors left, and they're the only 2 I have left, and they're 2 watt. I think these are actually 3 watt metal film, 2.2K. We'll put those in. I may also do the 3 transistors, but I'm going to wait and make sure that I have the correct replacements for that. Okay, I'm just about finished with the board, and I'm just trying to decide whether I want to replace these transistors or not. I'm looking at the circuitry. These 222 or 2.2Ks have been replaced, and they were bad. And as you can see, they are the bleeder resistors for these caps. So that would not be a good thing if they were bad. Now, the AC sense circuit, which is part of the protect circuit, comes off of these two little diodes, these 1N4003s. You can see they come together here, and it gives you this, they have this 22 microfarad 63 volt cap, which of course if that goes bad you'll get a lot of ripple right here, which would probably mess this up from being able to come in. But a little more curious is you have this 470K resistor, and on the other side of it you have a 220 microfarad that's only rated at 6.3 volts. Now when these two transistors are functional, what's going to happen is you're going to put that voltage up here across this resistor. This resistor is going to divide with these two transistors that are kind of in a Darlington pair. So you'll have two voltage drops here. So you only have about 1.5 volts from here to here. So theoretically this should never get above 1.5 volts. However, if one of these transistors should open up and then you don't get this path from here to here, that voltage, which is going to be, you know, upwards of 60 volts or so, is going to all, because this resistor, it's going to be high impedance, this capacitor will theoretically be able to charge way above 6.3 volts. And it would trash this thing in pretty short order. Even though you have this 470K, all this is going to do is act like an RC time constant. It'll make the capacitor charge up more slowly, but it's still going to charge to a much higher level than 6.3 volts. So this is another bad design in this amp. There's a lot of these little mistakes that I see throughout this entire amplifier design. And we're looking right now at the first revision of it, you know, because the original schematic was so blurry you couldn't really see it in the manual. I mean, you can't read any of the letters or anything like that. But this and this are identical in the early model and the mid model. Now, in the newest model, they had made some changes, and I'm not sure if they did anything. They definitely did some changes in the power supply by mounting the board up here and everything. So, some interesting things. This is a really high gain circuit, and all this does is when it triggers, it pulls in the relay. This is the one that actually senses your DC offset from your speakers. And of course this is your filter, your input filter, and we talked about this when we did the video on when I did that video on speaker protect circuits. I kind of talked about how this works, so I don't need to repeat myself on that. So this transistor is pretty critical to sensing the input. So this one I might replace. These two are working fine, and I don't see any reason to replace them. So this one's probably going to get replaced. But first of all, we have to figure out what kind of a suitable replacement we can use. Alright, a couple of you commented about noticing the Tektronix 576 curve tracer, and yeah, I got it out and set it up on this bench. I'm actually going to make this desk over here a test equipment desk for like component testers, like my vacuum tube tester, my curve tracers, my capacitor analyzers. All that stuff's going to go over here eventually. And the reason you don't see this very much is this actually is a really nice example of a 576 Tektronix curve tracer. It has been taken care of by Tektronix throughout its life, but it has kind of been sitting for a long time. It has a few issues with it since it was taken out of service, and that's when I got it. And I can tell you that it even has this is an early serial number model, which those were notorious to have problems with the high voltage transformers. But this one has the original factory upgrade from Tektronix of the new black transformer. Those of you who know about these will understand what I'm talking about. There was someone that took it upon themselves to design and make their own custom replacement transformer, but I don't know that you can buy those from that individual. And these new transformers, you know, that came as an upgrade from Tektronix are rarer than hen's teeth to find. But this one fortunately had all that, so it needs nothing. But it does need some work. Some of these displays are kind of flaky, the little bulbs in there. It's going to need some work, and down the road when the spirit moves me, I'll probably fix it, but not in a big hurry. But anyway, what you're looking at right now is the original transistor that's in there, and I can't remember what it is. It is a SPS 439. There's not a whole lot of information on those in here. That'd be this one right up here. And you're looking at the curve trace of it, and right now I have it set according to the dials. Let's see if I just give you a quick explanation. And this has been running for a while, so it's kind of drifted a little bit with temperature. But each one of these steps, for each step, that represents 10 microamps of input current from the, you know, from on the base. So your base to emitter current is, for each one of these steps, is 10 microamps. So this would be a 10 microamp step, 20, 30, 40, 50, and so forth. So you first have to know that. Then the vertical output is set to read 2 milliamps per division. So whatever that step goes up to, we know that we have 10 microamps per division or per step going in. All we need to do is measure the amplitude from ground here from the bottom to find out what the output current is. So for instance, I'm going to look at step 5. So step 1, 2, 3, 4, 5 is right here. And you can see at step 5, at 10 microamps per division, that would be 50 microamps of base current. And if we count the divisions, 1, 2, 3, 4, 5, 6, 6 times 2, that's 12 milliamps. So with 50 microamps input, we're getting 12 milliamps output. And if you divide that, so you divide the output by the input, you're going to get, you're going to find out that that's a gain of 240. So your beta is 240. Now, if I switch over to the other one, to the one that I found that's a close match, 1, 2, 3, 4, 5, if you look, it's just a little bit higher. It's right about 14 milliamps output. And with 14 milliamps of output and 50 microamps of input, that comes up to a gain of about 280. So you can see they're very, very close to one another. And so this is about the closest match I could find. And let these cool back down. About the closest match I can find. Now here's some interesting things. What I ended up finding was the closest match was a 2N2222, which is a really basic transistor. These were actually pretty common back in this day. A lot of the jukeboxes and things that were out there at the time, the amplifiers, used weird Motorola parts like that, and they ended up crossing over to 2N2222s, or sometimes ECG 130s, and so forth. So let's just see for the heck of it what a KSC 945 would do, because everybody seems to have those, right? And if we plug one of those in place, there we go, you can see it has a lot lower gain. And I mean, I don't even have to do the math. Here's 1, 2, 3, 4, there's your 5th step. And you can see we just have 1, 2, 3, 4, 5 we're not even at 5 divisions. So that's not even 10 milliamps output. So it's a much lower gain. And if we go to, let's see, what's this one? This is a 2N5551. If I plug that in, it's a little bit closer, but you can see what the curves look like. And when you look at the voltage at each step, and we have 1, 2, 3, 4, 5 is up here, and that's about, well, that's 2, 4, 6, 8, 10, 12, maybe about 12.5 milliamps. So it might work, but that 2N2222 is a pretty good match. So what you're going to find in these is a lot of the transistors in here, there probably are going to be modern replacements, but you have to be sure you get the correct gain, and they're very picky about it. If you look, they even give you a gain chart. Unfortunately, Q301 is not shown in there. These are mostly showing you for the amplifier board, but you can see the color or the dash number that's on the transistor tells you what gain level it's going to be, what gain range. Like for instance, if Q804 has a yellow dot on top of it, paint dot, that means that its gain range is anywhere from 70 to 99. And if we go over to the amplifier module, you'll see here's one with a yellow dot on it. I don't know if you can see that right there. And this has a yellow dot on it. So these are all in that range. Very important. And as long as you get them in the correct gain range, having them be completely, totally, perfectly matched probably won't be as important. Of course, it would be optimal if you could get perfectly matched, but the main thing is you want them to both be in that same gain range. As long as they're plus or minus within that range, they're going to be just fine. So anyway, I thought some of that would be interesting, and I'm going to replace this transistor with a 2N2222, and we're going to put it all together and see if it works. And just to show you something a little more extreme, here's our original transistor that came out of the power supply board, and here's a KSC 1845. You could see it's off the charts. So it's much higher gain. So you can't just drop in any transistor. That's the important thing to take away from all of this. You do have to test them. And you can use those little testers. And you've seen me use them before, like this little thing. So let's see if we're right. Okay, let's go to this transistor right here that we were originally testing. And we calculated it to be somewhere around a 240 gain or something like that. Let's see what it says. And it says it's much lower. It's saying it's a 152. And that's because of the range that it's testing it at. So we don't know what the current is. We know that the emitter current is 6 milliamps, and of course we were checking up at a much higher range, so the gain was different. So you can see even these little testers won't tell you the whole story, and this should read a much higher gain, but again it won't read the same as the curve tracer. Depends what step you're checking. You can see this one's a gain of 376. Your current is 3.43 mA. And your ICEO is 0.05 microamps. So you could see these are more limited as to how much current and voltage and so forth they can apply to the transistor. So even though they'll give you a rough idea, they kind of won't tell you the whole story unless you put the transistor under load. Now, I don't use this yet because it needs to be worked on, but I have my Medel or what is it, Circuit Specialists tester, and I also have the homemade one, curve tracer, so I can use those. And of course I have my little matching jig, and those work pretty well for matching. But anyway, let's get back to it. Okay, the amp is back together, the power supply is done. I replaced the capacitors on the board. I replaced the one input driver transistor for the overcurrent sense. I have the bleeder resistors replaced. All the other resistors have been tested and are good. We have our new relay in. We've determined that we're not going to change out these diodes yet until we have a suitable replacement, or maybe not replace them at all. And I replaced the filter capacitors, the big ones. And if any of you are interested in what they are, this is what I put in there. They're Nichicons, 33,000 microfarad at 63 volts. And they're very good capacitors. And I have them all installed. Everything should be ready to test. I've not touched anything on the amplifier modules yet other than what we just talked about. I have my connections back up there to check our input, or our idle current. And I just realized I did not connect the dummy load yet. I want to put that on. I have the current limit set to the smallest bulb, so it's only like a 50 watt or 40 watt bulb. So this should take a long time to come up through that bulb. Matter of fact, if it's going to smoke, let's catch it on video. So here we go, turning on. Okay, very bright, but dimming down. Excellent. Okay, let's come over here and let's see if, yep, amplifier starting to conduct. We have 1 millivolt. We want to have about 20 there eventually. And the protect relay came in. Perfect. Okay, let's go to a bigger bulb. All right. And it's still looking good. And let's go to yet an even larger one. And right there's our 20 millivolts where we left it, 22. Okay, let me connect my signal generator. Now while things are booting up here, a couple little notes. Number one, we did not have to change that transistor. I did that as a practice to kind of go through. A lot of you have commented about the transistors in these, about matching, about all these different things. I wanted to go through the process of just at least replacing one, because so far none of the transistors look to be bad. Yes, there are problems with the design of this version, this first version of this amplifier, that we should probably address when we do the amplifier portion of this video. But I'm not going to get into that, like I said, in this one here. And you can see this is burned really bad and it's welded, but this side, which was luckily connected to the one side, still works. And that's why we were able to, the protect circuit was able to kick in and out, you know, when we lit up our bulb and kind of hit the we were clipping. All right, let's get on here. And I'm gonna turn on a little bit of a signal, and that's good. And you can see I'm getting, my bulb is lighting a little bit. So let's go to, that's normal. Okay, and that gives us a little bit more headroom there. So let's see if we can put a little more power through it now. Alright, that's about 15 watts right there. And if I go much more, we're going to trip the protect. Let's keep going. Should go any minute now. There it goes. So you can see it kicked off. So it's working. Alright, here we go. We're pushing our luck now. 20 watts, 30, 40, 50, 60, there's about 80 watts right there. So, and I'm off the leash right now, so I don't have any current limit. All right, so let's turn the signal generator down, turn that off, and let's see if this will drop back down somewhat to a reasonable level. And you can see it's dropping pretty rapidly. You can see our bias circuit is working. And this is going to take a little time to drop it back down because of all the heat that this thing was producing, but it will bring it back level, and it will take our bias right back down to that 22, 24, whatever millivolts. So there we go. So let's see. Yeah, we got a little bit of heat on it now. I can feel the heat sinks are warm. And I had it running at about 20 watts for a good while. And then we just ran it up to that 80 watts that you saw. And I think we're good. So I think we've achieved success, and we're ready to go and start working on the amplifier modules themselves. Again, I haven't decided what I'm going to do yet. I do know a few things that I will definitely do, but as far as the bias circuit is concerned, I don't know if I'm going to rebuild it, if I'm going to stick with the poor design and just put new components in, or what I'm going to do yet, but that will be determined in the next video. So that's it for this one. Until next time, I wish you all peace, joy, happiness, and good health in your lives. And little by little, we'll see this amplifier come back to life. All right. Take care, everybody. We'll see you again soon. Bye-bye.